So yeah, I'm a software developer, I'm a consultant, I do a number of different things. But one thing I really want to clarify in the very beginning, I am actually not a Rust expert. I remember when Dave asked me a while ago whether I could do an introductory talk to Rust. I thought, okay, I'm not an expert, but maybe that's not even a bad thing, because I'm going to run you through a journey of how I approached Rust as somebody who has done programming in a fair number of languages, probably 10 languages commercially. So this is a bit of an introduction of my personal journey, how I learned it, and I hope I'll show you a fair amount of code and give you an introduction. The other part that scared me slightly more was Rust is a big language with a steep learning curve. And I thought, how much can I do in 45 minutes that gives you at least an overview, a flavor of the language, and how much, and that is my goal, how much can I inspire you that when you leave the conference tonight, that on the weekend, you're going to do some Rust programming yourself. So that is my goal for this talk. Let's start with the why. You probably read the text, which is why all of you arrived in the room. In the introduction, when I wrote it, I said it won the Most Loved Programming Award 3 years in a row. Now the new StackOverflow survey has come out and has won again. So 4 years in a row now, the most loved programming language. And I noticed that there's a lot of good community around the language. I wrote a blog post a while ago about my first impressions, and the community was extremely helpful. They corrected some of my mistakes in a very nice way. They gave really good hints, and I can see that there's a fantastic community. What is interesting, though, is also how popular is it? And I'll spare you the searching. It's a good bit further down, so it is really quite down there. I think this might be changing in the next year or two. At the same time, though, please bear this in mind. Rust is a large language. It brings a lot of modern concepts that I hope I can highlight to you, but it does have a steep learning curve. And that, I guess, is what we're seeing here. A lot of people see the learning curve, they turn away, they use different languages, but the ones who go over it, they really see the power and they see what you can do with Rust, and they love it accordingly. Why are many companies interested in different programming languages? I mean, what do these three companies have in common? They all don't like C and C++ very much anymore, to the point where they all came up with their own programming languages. I'm not going to talk about the other two. I'm going to focus on Rust, obviously. But I do want to give an example from Apple to start with. And this is when I wrote some of the slides in the summer. This is from the then current, the knowledge base article that accompanies a security update to macOS. And they are alphabetically sorted. You see it starts with Apple Graphics Control there. I'm going to skip 2 Bluetooth vulnerabilities, but the rest is really right from the document. And what we're seeing here is 3 of those ones have to do with memory-related problems. Next page, I'm not skipping anything. The next 4 actually, also memory-related. We're on page 3 now. I'm just scrolling through memory-related problems. So what we're seeing here is Apple as a company that writes an operating system, and as you can see here, many of the tools in C and C++, I would say you can say the vast majority of the problems are caused by memory-related issues. And that, of course, is a big problem for a company that has software out in the wild in the numbers. And then you might say, okay, we've talked about a couple of the Silicon Valley companies. We talked Apple as one of the big operating system providers. What about the company from Seattle? And that is what they are doing. This is an article from the summer, from the obviously Visual Studio magazine. And they are saying they're eyeing Rust now because they have so many bugs. This is actually based on some research, and I'll give you a quote to read. The QR code is to the article. It is actually worthwhile reading, or if you download the slides, of course, you get the URL. But again, what they're saying is the vast majority. In the article, it is very clear. It's about 70% of the problems are caused by memory corruption issues. Personally, I got interested for a different reason. I work in Germany. We have a lot of manufacturing, automotive companies. We're seeing in all sorts of areas much more powerful embedded devices where the software or the hardware is not the product, where it's embedded in something else. And again, here, what we're seeing is there's a big need for having a system that is more secure, that provides more safety than C and C++, but at the same time doesn't come with a garbage collector, and is very close in performance to C and at the maximum performance you get out of the hardware you have. With that said, again, my goal is to inspire you to get started, so I want to show you it is actually very simple. The first step you do is you're downloading something called RustUp. You download that either directly or with a curl command, and I understand the security implications, but once you have Rust up on your machine, it installs the entire compiler toolchain and all the tools you need, and it can be installed in your home directory. You don't even have to have it on your system. And what you can see here on that screenshot, you can see how the Rust up command can be used to update the entire toolchain on your machine. It is actually quite frictionless. I mean, it is exactly what you expect from a modern programming language, but it is good to see that you're getting that. Very similar. It comes with a tool called Cargo. That is the dependency manager and general build tool. You'll use that for almost everything when you work on the command line. If you're working in an IDE, that will probably call Cargo under the hood. What we're seeing here is standard stuff that we're expecting today from modern programming languages. Simple scaffolding, I'm saying Cargo, new, creating a new application that is called Hello Rust. And it creates only 2 files. Again, it's very, very simple. It's a main file that will compile directly into a binary. So what you know from C, C++, but also what you know from languages like Go, it will create one executable file. The only other file we're seeing here is a cargo.toml file. Think about package.json, think about gem files. This will declare some major attributes of your project and most importantly, the dependencies. I will not, I remember I said, like I thought about how can I get a whirlwind tour of Rust into 45 minutes. I will not do Hello World. What I'm actually doing is I'm using an example that I use to learn Rust. If you were in the keynote last night about genetic programming, this is actually, it doesn't matter for the purpose of this talk, but what I wrote is a simulator of genetic programming in artificial life. This is reasonably interesting code because you can focus mostly on the algorithms and not so much on websites and user interfaces or database access. And I'm using examples from this code base. All you need to know is this is basically a simulation of creatures that are running around in the world. They have a program that encodes their strategy, and they can interact with each other, and they can eat food. That is roughly the idea. So agents, creatures running around in the world. What is interesting to see here are a couple of things. It is not immediately, obviously, but in that section a bit further down, in the dependency sections, you see a dependency on Chrono. Chrono is the date and time library. So Rust went down the path of saying, we want to have a small language, and we do not come with a large standard library. That is an approach that we know from C, but also from JavaScript. So even date time doesn't come standard. You can use Chrono. You can use another library too. Sometimes there is a bit of a mixed blessing. I remember when I first did this, I was like, where's the date class? Couldn't find it. And then I had to go through a Reddit thread to figure out which ones is the current one to use, or which one had which advantages. But again, it does help you. Similarly, in line 11, you can see something called cert. You'll see that quite often. It stands for serializer and deserializer. So even the serialization, deserialization is not part of the language. You can choose that one. And what you see further down in the dependencies is this desire to make Rust very modular. So you can see in the next line, I'm declaring a dependency on cert JSON. So the JSON binding I don't have to do if I don't want to do JSON. And again, that comes back to building small binaries, building binaries that have a small attack surface also, right? I mean, you could say, never mind, we'll include JSON and gRPC and all sorts of other serialization formats. In the binary, the bytes on disk don't cost that much. But at the same time, the more code you include, the more potential security problems you're also including. So this is something that is really at the heart of Rust, that they're trying to make small libraries that are composable. You can take it a step further, and you can see this in line 14 down there. I'm declaring a dependency on UUID, a generator for UUIDs, and that one even has a feature for cert. So they know, sometimes the libraries know about each other, and I'm saying I want the UUID library, and yes, please, I do want to serialize and deserialize UUIDs. This might sound a little bit extreme to you, but if you are doing systems programming, if you're trying to write small binaries, or if you're extremely concerned about safety, say in the automotive industry, that is really a very, very positive trade because you are really reducing the attack surface. One thing that is also worth highlighting on this one here is in line 5. It specifies an edition. So this is Rust 2018 edition. Rust, like many other modern programming languages, was released before it was released in an early version, let's put it that way, and has improved over the years. What I really like about Rust is that it can specify the edition. I can use today's tools to compile old source code, or I say I want the 2018 edition, and then I get to use the new features. That is, in my personal experience, in stark contrast to something like Swift, where you sometimes have to go back to older IDEs or even older operating systems to actually compile the code that you wrote only 3 years ago. So again, they have a relatively good approach to evolving a language over time with explicit additions. The last thing, I guess, I don't know whether you noticed that whether there was an accident or not, but I'm showing this in IntelliJ. I'm actually using IntelliJ to write Rust code. My normal go-to IDE is Visual Studio Code these days, but I have found through experimentation that the current versions of IntelliJ support Rust even better than Visual Studio Code. So it is worthwhile looking around. There's a lot of refactoring that actually already works. There are some refactorings like inlining that still don't work, but I'm pretty sure the lovely folks at JetBrains will get there. So that is good to know. How does it start? Here I'm building this application. It's a few thousand lines of code. It's not big at all. And you can see while I'm talking, it does take some time. So it is like a C-based language. The compiler needs to take time. You're pulling in the dependencies. We're compiling them. And you can see that after about 20 seconds, it's done. The good news obviously is, like any modern system, it has an incremental system. So once you repeat that build, it's going to be much faster. It will only have to recompile the files that you have changed. It is worth noting, though, it is the debug build. So this is instrumented and not optimized. So that compiles faster. At some point, and I'll come back to at the very end of the talk, at some point you want to make a release build with lots of optimizations. It's totally worth it, as you will see it, but that takes a little bit longer. The good news, though, is the testing that is built in, you can see how it needs to compile a few of the tests, but then you see a first glimpse at the execution speeds. The tests are really running through faster than the terminal can scroll. And in my personal experience, the incremental compiler combined with the really fast execution of the unit test never really got me out of the flow of developing. I'm very sensitive to this. I don't like to have an idea. I do test-driven development. I'm not going to show you anything about TDD in Rust today, by the way. I love test-driven development, and I have this red-green refactor cycle, and I did not feel that the compile speed really did hinder me. Most of the time, obviously, I would not compile this on the command line, but would use the IDE to do that for me. OK. Let's get started with some real Rust code. This here is the structure for the world. I mentioned in the simulation we have a world which is inhabited by creatures. The first thing you will notice, I guess, is the brevity. Rust really likes short keywords. In line 15 at the very top you can see pub. It's not public, it's pub. A bit further down you see impl. It's not implementation. FN, not function, and so on. So there's this brevity that goes throughout all of the Rust keywords, and I think also into the libraries, and that also affected me. I'll come back to that in a minute. What you see first is that we have a struct, which is a structure that can stand alone. For those of you, oh, by the way, how many of you have programmed in C? Ah, OK, that makes it easier, but I don't want to rush it too much because there were a good few hands that didn't go up. So I need to find a balance, of course, not boring the people who know C, but also not like speeding too much. But anyway, so a struct is just the data structure. It's not really an object-oriented approach. And then further down in line 24, we see the implementation of the world. I can attach an implementation to the structure, but I don't have to if I don't want to. So it is kind of an object-oriented language with some quirks that I'll show you in a minute. What is interesting here, though, we see the name of the world is an option of string. So Rust is one of those languages that has a proper option type and thus avoids a lot of the awkward null handling that we see in many cases. So name can either be none, which would be null pointer in many languages, or it can be some of my world. And there's a lot of syntax built into Rust, and a lot of the libraries use it in a very clever way to avoid this constant null pointer checking and so on. So it is just much more embedded in the language. What we also see here in line 25, even the constructors are kind of a convention. So most classes, or when you are attaching like implementations to a structure, you create something called new. And here we also see, for those of you who have never seen Rust, the first function declaration. So we're declaring a function here, a public function, with a name new. The first parameter is called name. The type of that parameter is some kind of string. I can't go into the depths of all the string handling. Just take it, my word for it. It's some type of string. The next one is called params. And you see how I'm impacted by the brevity. I didn't call it parameters. I called it params. And that is of type params, which is another structure that I define elsewhere in the source code. And the return type is a world. it's another structure. So this is how we declare functions in Rust. The actual creation of a struct has its own special syntax, and you can see this here in the highlighted area. We can just write the name of the structure, and then in curly braces, we can actually initialize that. This is also the return value of that function. In Rust, there's no return keyword. You don't generally write return. The result of the last expression in a block is the return value. So we don't say return and then the construction of this world structure. We just say world, and that is being returned. Things to highlight here is we can see that in random and log, we see that I'm also using this convention for constructors. So the random number generator, I'm calling new on, and the log file or the log that the world keeps is also just initialized like that. And then it is worth highlighting, Rust is a language that, if in doubt, looks at developer productivity even when it increases the learning curve, at least in my experience. So there are a number of shortcuts that you don't have to put in the language and that make it harder for a novice that first reads Rust code, but in the long run makes it easier to write Rust code. So what's happening here in those two lines that are marked up with the arrow, this is a shortcut. The field, as you can see further up, is called terrain. The value I'm initializing with it is also called terrain. You can see that in line 26. I'm declaring this variable. I'm saying let terrain, and I create a new one there. When that is the case, when both the field and the parameter are the same, I can just write them in a contracted way, and I'm just saying terrain and params as here. I'm highlighting this not because it's super important to know, but it gives you an idea that the designers of Rust really went for the long term. They went for the long game, making it easy for people to write large amounts of code, even when it comes at the expense of maybe making it a little bit more difficult or unintuitive for people who are new to the language. A bit further down in the world implementation, we see this function here called doCycles. And it runs a number of cycles of the simulation, namely num cycles. You can see that there. Oh, sorry. You can see that further there. There's num, which is an unsigned 64-bit integer. Again, the brevity. And I'll tell you, you will get to know all the different integer types. There's 32-bit, there's signed, there's unsigned. You cannot multiply them because of safety concerns. You often have to cast them or do other explicit ways of doing it. You will get to know them quite well. What is worth highlighting here is the first parameter. We are passing in self. Some programming languages do this. Python, for example, also has a visible first argument of the object on any method, basically. So what we're seeing here is this is a method, and it's a method, not a function, because I'm passing self, or this in Java speak, the object itself in as the first parameter. Gloss over the ampersand mutable. We'll explain that at a later stage. You also see the trimmings of many other modern programming languages. We see ranges there, for example, num. So ranges are first-class objects. We also see the underscore in the for loop there, which is like, you know, it would be a variable, but I don't need the variable. The compiler would warn saying you have created an unused variable, so I can say underscore. Again, there's syntax in there that is really very useful when you know the syntax to write better code, but it is syntax, it's baggage, if you will, that you first have to learn. You have to know that you can say underscore, and you don't put I in and then forever are upset about the compiler warning you that you're not using I. And then what we're doing here is we're saying self, which is the reference to the structure, and we're calling another method on it called doOneCycle. So I mean, you see that that function is actually, or that method is actually very trivial, but it's a good introduction. This was, in many ways, a bit of an object-oriented view on Rust as a programming language. On the next slide, I'm trying to show you a more functional approach, which Rust also can do quite well. So here, we have a method in some helper class called cycleCount. These little creatures that are running around have a set of instructions that defines their strategy, like move and eat and turn left, turn right, and so on. And each of the instructions have a number of processing cycles that they can take. So what this function is trying to do, tries to calculate how long it would take to run the entire program. Somewhere else in the system is this table here. And it says the eat command takes 10 cycles, move takes 5 cycles, and so on. What is super interesting about this one is Rust does not have literal arrays or literal maps in the syntax. Rust does have a powerful macro system. So you didn't see that because I didn't highlight it. In the dependencies, there's something called map literals. So I'm declaring a dependency on that, and I can even change the syntax of my source code. I can write hashmap exclamation mark, and then the macro creates new syntax that allows me to have a literal dictionary in my source code. I think that's going to be quite fun for the IDE designers, and you can also already see that IntelliJ, for example, has issues with this syntax because it is not the original Rust syntax. It is created by a macro. But again, it's a powerful mechanism, and this is like a mini DSL, if you will. And I can see in large systems that these kinds of DSLs are super helpful. Anyway, back to that function. We are trying to get a list of these instructions, and we try to sum up the instruction count, the cycles it takes. How do we do that? We do it in a very modern functional way. So first, we get an iterator from the program. Program is just an array. You can see this declared in the previous line. After that, we do, for those of you who know functional programming, a simple left fold. So we will go over the array, and we start with an accumulator of value 0 that is highlighted there. And then for each element in the array, this anonymous inner function will be called. You can see the two parameters called accumulator and instruction. They're being passed in, separated by the pipe symbols. And after that, we see the body of the anonymous function, which basically takes the accumulator and then adds the instruction of that, the cycle count of that instruction. And it returns it again, of course, no return statement. This is, I think, so obvious. This is even in languages like Java, much like that. Luckily, unlike Java, you don't have to collect things at the end. It just becomes a regular object at the end. Again, Rust is building on the primitives and are creating higher order abstractions. So this is how you would actually write it. So you would get, again, the iterator, but in the end, you would have a map function. And that, of course, simplifies the anonymous function that you have in there. So rather than having the accumulator and doing the addition yourself, you're just saying, I want to map from the instruction to the cycle count, which is what the highlighted area does. And then at the end, you have the sum, which will take a stream of data and will just sum up all the values. I guess that's pretty much par for the course in modern programming language design, but it is good to know that Rust has both these flavors. You can write relatively object-oriented code, but it really also very well supports a more functional style of programming. And I guess the value really lies in being able to pick both of them as you need them. Right, now the more difficult part about Rust, but one of its absolute key features is memory management. So in most programming languages that we see today, even newly created ones like Go, for example, we find garbage collectors. They have a number of huge advantages, but they also have the disadvantage of being a garbage collector. They may pause the execution time. They may cause other issues. So Rust went with an approach that doesn't do garbage collection. The standard approach in that case is either nothing, like leave it up to the developer, like in C, and we know the results from all the security problems. Another approach can be reference counting. That is what we see in Objective-C, for example. We see in Swift to a certain extent. It's a bit more complicated. They didn't do that either. They were the first ones to came to market or were able to take a new concept called borrowing that had been around in academia for a while, but create an implementation with small enough overhead that it becomes practical to use. And I'll explain to you how that works. This here, these slides with a white background are copied straight from the Rust book. The Rust book is a website. You can also buy it printed. They have explained this really well, so why would I create new examples? What we're seeing here is a block, and we are creating a variable called s. And as long as s is around, the memory to hold the string hello is kept in memory. The moment s goes out of scope, the memory is released. So I don't have to say I want to retain you or I have multiple references. It is really just as long as the variable that owns the value is in scope, the memory is kept. The moment the variable goes out of scope, the memory goes away. You can easily, immediately think, how the hell is this going to work? So what happens here is I have s1, which I'm creating with the string, and now I'm saying s2 equals s1, as in I'm assigning it. And now you're like, okay, who owns this thing now? In most languages, this would be unclear. Automatic reference counting would probably have now 2 references. Not so in Rust. Rust has a clear ownership model, and only one variable owns the value. And when that variable goes out of scope, the memory disappears. This has the little question mark and the crustacean here on the side to say this is actually incorrect code. It will not even compile. What will happen is in that line at the very bottom, when I'm trying to use S1, the compiler will say, you must not use S1 anymore. You don't own this anymore. S1 has become unusable. You have transferred the ownership of that string into S2, and after that, S1 cannot be used. So it is very clear there's always one owner of a given value. Now you might think that's really super awkward if I want to call a method, right? If I have a method like this here, or a function, to calculate the length of a string. If I'm passing it in, I'm giving up ownership, and then I can't do anything with S1 anymore. That really sucks. I don't want that. So what they have come up, and this is the concept I mentioned earlier, the idea of borrowing. If you have done C, this is basically creating a pointer. I'll explain that on the next slide in a bit more detail for those of you who don't know C. Basically here, and it uses the same syntax as in C, I'm doing ampersand S1, I'm borrowing the value for a moment being. I'm not taking ownership. S1 is lending me the reference, so I can work with it for a while, and when I'm going out of scope, S1 can be used again because it owns the value. And this is exactly what happens here. So calculate length only gets the reference, it gets the borrowed value, I can do something with it, S goes out of scope, and now I don't have a reference anymore, and S1, of course, is or has always been the owner. So far, so good. For those of you who don't know C, I'm going to give you a very, very brief explanation into how those pointers work. It is illustrative only. This is not how Rust or C or Intel actually really works, but the idea is the same. So what you have is, when I declare a variable like this, let message be get message, and I own this. That variable owns the block of memory you can see in the memory dump here. It is like the hex values, and on the right-hand side, you can actually see the ASCII values, and you can see the message there. So this is what happens. When message goes out of scope, then that block of memory that is circled in blue here, that will be reused by the operating system or the runtime for something else. What does this do, though? Because I mean, I'm very aware that in Java, you always think about, you just kind of point to something and it's there for you. But here, the message really owns that block of memory. But what is the pointer? That message reference, the borrowed thing. What that is something like this. It is just an address in memory. It is a pointer to the actual block. And you can see this here, this 0069674 is the address you can see in the memory dump on the left-hand side at the corner of the blue thing. So when message ref goes out of scope, that little bit, those few bytes, that was the value, they get reused. They wouldn't be on the heap like I'm showing here, they would be on the stack, but you get the idea. When the reference goes out of scope, it is only the pointer itself. When the value itself goes out of scope, the whole data structure behind it disappears. There's a second very important concept, and it has to do with mutability. That also is one of the factors, together with the memory model, that really increases the safety of Rust programs. So I'm creating a string here, S, and I'm passing it to a function called change. I'm creating a reference. The function borrows the value. I'm still the owner. And the change function tries to do something. They borrowed the value from me in good faith, but they're trying to change the value. And that will not work. The compiler will not let you change the value. It has a deep understanding in the language of what is mutable and what is immutable. This will just give you a compile time error on the line that says some string push. Push string is known to mutate the value and says you just got borrowed a reference, you cannot mutate this. To fix that, or if I wanted to show you how it actually works, you would do it like this. You have to create the string as mutable in the first place. So the value needs to be mutable. And then not only that, I still, in addition, need to create a reference that is also a mutable reference. You can see that when I'm calling that change function, I'm saying not only ampersand to create a reference, I'm saying ampersand mute. I'm creating a reference that will allow the the function that gets the reference to actually mutate the object. And this code then compiles. And now I think, okay, what the hell? If I can create a mutable reference, why aren't all references mutable? They've thought about this, and this, for example, does not compile. So I'm creating in R1, I'm creating a mutable reference to S, and I'm trying to create a second mutable reference. The compiler will not let me do this. it will only allow me to create one and only one mutable reference. And if you've done programming where you really had to push data between multiple threads, I guess you immediately understand why that is a super beneficial feature. Because a lot of the problems occur, and I don't know whether you were in the TLA Plus talk, a lot of the problems occur when multiple threads are working on the same data because the sequence is unclear, you don't really know what is what anymore. So the mutable references you can only have one and only one of. The compiler will simply not let you do this. You can have multiple immutable references, so R1 and R2 in this case are totally fine. You can't create a mutable reference when you still have immutable references around, because again, you can't predict the behavior anymore. In this case, I'm giving R1 to one thread, R2 to another thread, and R3 I'm doing something with. At no point do I really know what the value is that R1 and R2 will be. So you can have either one mutable reference, one and only one, or, and that's a real strict or, many immutable references. Nothing else is allowed. Many immutable ones or one mutable one. And the last thing I want to show you where they really went quite far with the analysis they can do at compile time, dangling references. So if you look at that method down there, the dangle method, I'm creating a string. S actually owns the memory, as we discussed in the previous slides. It tries to return a reference to S. But I guess you now know what happens, right? When that curly brace closes, S goes out of scope, the memory is released. Whoever gets the reference back would now have a dangling pointer. They would have a reference to basically nothing or a random thing in memory. This doesn't compile in Rust. The Rust compiler understands the lifetimes. There's a whole talk you can do about lifetimes in Rust. But on the basic level, it understands the lifetimes like this and says, the lifetime of S is shorter than the lifetime of the reference you're trying to create, and therefore I will not allow you to create a reference. The lifetime of a reference must be shorter than the lifetime of the thing you're referring to. Did that make sense? Good. It sounds relatively simple. I'm going to show you some real code now, and you'll probably feel like I did and many people that I talked to who learned Rust, something that is as simple and positive. I mean, I don't think anybody would disagree with this, right? It makes total sense. But when you start programming with it, it really does take a while to get used to it, shall I say. So let's get back to the creature example. We have a function here called do with creatures mute, ignore the mute for now. So basically, I can tell the terrain, I will pass you a function, and please call this function with every creature that is in the terrain at the moment. So that function called func, func, that I'm passing in here, that will be called by the implementation of the method we're seeing here for each of the creatures that currently lives in the world. The terrain knows it, not the world. That's the design. You can see it's clearly a method because we're passing in self. And then you might wonder if you've done programming, you see like this generic syntax, right? The greater and lesser than and f, and you're like, okay, Rust is totally typed, but the function is only f. What is f? What are the constraints on f? And it would look really awful in many cases to try to squeeze the declaration of the function into the declaration of this method. So what you can do, like in languages, I've seen it in C#, for example, you can spill it out onto a next line into a different phrase. So basically what I'm saying here is that function that you're passing into this method, the function that will be called later, that function has to take a terrain, it has to take a creature, it has to take a tuple. That's also a nice thing in Rust. You can have tuples, you can see the round brackets, 2 unsigned 32 integers in there, and it returns an option of a tuple. So here I'm now in a completely separate space declaring the constraints of the functions that need to be passed in there. Again, you can see like a lot of the things that you saw before, like options, for example, they can be combined with everything else. All these concepts are generally orthogonal. What this function generally does is it processes the creature a little bit, and the tuple is the coordinates, where is the creature in the world, so it can find its neighbors, and the return value is an option. If it's none, the creature has died. If it's some, that is the new place where the creature wants to be in the world. Now, flicking over to the world, and this is now where it's getting interesting with the memory model. This is how this function is being used. So there's this function in the world class to process all the creatures. And it says self-terrain. That is unsurprising, I guess. Do with creatures, that's the method signature we looked at. And then it passes in this anonymous function. And it does take the 3 parameters we saw on the previous slide: terrain, creature, and position. This is a closure, common in many modern programming languages. And like in many other programming languages, if you look at it a little bit further down in that if statement, I'm saying if the creature's age is greater than the creature max age that is defined in the world parameters, then I'm returning none. The creature dies after a maximum number of cycles. And what I'm doing here, I guess you see this, I'm using self, right? I'm using self params. That's a variable, a field that is in the world structure. So I need to capture that in the closure to be able to use it. If you think about safety, though, I have no idea what the function that I'm calling, the do with creatures, does. It could capture this, it could keep it around forever, it could pass it to a separate thread. So there clearly need to be some rules what happens with the capture. And at least to my surprise, this didn't even compile. It gave me this error message. And this is actually a genuine Rust compiler error message. They are very long, they're designed to explain very well what happens, to the point of using ASCII art, as you can see there. And trust me, it looks a bit odd, but it really is helpful. It's actually in a number of other places further up there. It says error 0501. It's underlined. That actually is a hyperlink. In most IDEs, you can click on it and you go to a website from the Rust community where they explain the compiler warning. Or at the very bottom, you can see this. It says, I can even call the Rust compiler on the command line and say, explain this error in more detail than this error message. What I find slightly amusing is a lot of the documentation uses Game of Thrones references. I'm not sure how they feel about it now, or whether they're going to refactor it, but it's clearly in there. So, coming back to this. So we have this closure. What is the problem? What was the compiler trying to show us with this ASCII art? It is this bit here. As I mentioned before, in the closure, I'm using self, which captures self from inside the closure. But I'm also using self, the terrain, to just get access to my own field outside the closure. And that is what one of the error messages was about. It says, the closure requires unique access to self, but it can't have it because it's borrowed already. Remember what I said? You can't have multiple, you can't have mutable and immutable borrows at the same time. This is what it says. In the examples I showed you from the Rust book, it was very obvious. I think here, it takes really quite a while to understand what is really going on. So what I'm trying to say is there's some profound impact on the way you write code and the way you design code that is caused by the memory model. The good news is it forces you to think about what you're really trying to do. And the solution to this is the following. I am assigning the values from the structures that I own, the cycle count that is in my own structure, the parameters, I can assign them to local variables. Now, the closure can capture the local variables. And if it keeps this around forever, it doesn't matter. All it has done is that captured the local variables from here. The world structure itself can be used in a number of different places and have very clear ownership. This is something that a number of languages didn't get right, and I think Go has some issues in that space too, that you can create references, captured enclosures, and there is the potential of actually overwriting values because the ownership is not clear. Rust totally forces you to make absolutely explicit what the ownership of the values is. Parallelism is then almost a given. It becomes so easy because you have made sure that nothing bad can happen. And here I'm showing you one function from a different part in this simulation. Most of the time in these simulations, you want to run multiple at the same time. So this thing is called multiverse, so it runs multiple worlds at the same time. And I'm trying to figure out how many to run and how many threads I want to use. The computer I did this on has 8 cores, so I generally want to run 7 simulations so it doesn't crawl to a complete halt. And what you can see here is, again, functions are first-class citizen, and here it's very simple, right? I don't have to do. Remember I showed you the function and it says where f equals all of that. If you have simple functions, you can just declare them like this, right? I'm passing in this world function, it takes no parameter, and it returns a world. It's basically a generator for new worlds to be simulated. You can do it like that too. What is really interesting though is this bit here. This is all you need to do for multi-threading. You're basically saying thread.spawn. The 2 bars are basically an empty list. I'm not passing anything in. I'm cheating a little bit. I'm capturing tnum, the number of threads, from the outside. That works. But I'm using the move keyword. And what that says, you can see that there, right, at the beginning of the green box. The move keyword says, move the ownership of everything the closure has or tries to capture into the other thread. In the case of this number that I'm using, it will copy it over. So again, I can't have this accidental thing where this thread is now changing tnum and some other thread that also got it makes a change and I can't reason about my system anymore. I'm very explicit. When I want to capture something that I'm passing into a new thread, I can only move the ownership. The last thing I want to show you, because it's a nice summary of how all those features come together, thread spawn returns a handle. That's the handle of the thread that is spawning the other ones. You can see that there. And I'm pushing that onto an array. It's basically an array, but it has some nice convenience methods like push and pop. At some point, of course, I want to collect all those threads back together before I finish the application, right? How do I do this? You can see there, handles.pop. I can just pull it out. What is the pop interface in most programming languages? Because at some point, the stack is empty, right? How do you signal the stack is empty? Most of the time, by returning null. Rust doesn't really want to use null. It wants to use options. And what is really cool to see here is first the destructuring. I can say let sum of age equal handles.pop. If handles.pop returns none, this thing doesn't happen at all. If it does happen, if it returns something, because of the destructuring that you may know from JavaScript, age now is the handle again. I don't have to say age equals handles.pop, and then I have to say pull out the real value, or in Swift you would put exclamation marks to unwrap it, or call unwrap explicitly. I can use destructuring here. And even cooler, like many other languages nowadays, it can do this not only in if statements, but like in the functional tradition of Clojure and Lisp, it can actually do it in a while statement, and I can assign a new name to it. So the while loop actually keeps running as long as there's something on the stack, and as long as that's the case, it matches the sum and gives me the handle, which I can just close. And if it's over, it's a none. The whole let thing doesn't happen. The while loop gets a false, or I'm done with you, and can continue running. That is all, I guess, time allows as a brief overview of Rust as a programming language. But I do want to end with a small section. Oh, I highlighted there. With a small section on performance. What did that do? Interestingly, I mentioned earlier on this simulation I had written beforehand. When I wanted to learn Rust, I had existing code in Clojure. This, by the way, is a visualization of one of the runs. I mean, normally it runs much faster. You wouldn't want to see it like that, but it's nice to see. And I've written that in Clojure. I would say I'm a reasonably competent Clojure programmer. I had other Clojure programmers look over the code. It is idiomatic. The simulation there ran at about 110,000 cycles per second of each of the creatures. I re-implemented this really exactly in Rust. I literally took the acceptance tests of the Clojure version, copied them into a Rust file, changed it until it compiled, and then implemented the functionality. So I'm very, very sure that the implementation is the implementation of exactly the same problem. When I first ran this in Rust, I got to this, 3.5 or 3.5 million cycles. That's almost like 30 times as fast. That was what I was hoping for, to be honest. I thought, okay, I mean, I've done enough C programming myself. I know the speed up. I know that the Java VM is fantastic, but some of these things, because especially in Clojure, you have to copy all the dictionaries and so on. It's like, okay, that's probably not unlikely. What was interesting, though, I was running this from the IDE all the time. I was programming. And at some point, I remembered, yeah, it's running a debug build. What would happen if I do a release build of this? With all the bounce checks and the removed and the compiler actually being really optimized. And it ended up there. So 25 million. So it's a massive speed up, again, over the debug build. At that point, I will say, though, I noticed in the profiler, which I really struggled with, it's not like in Java where you have like 5 profilers to choose from and they're all nice and graphical. It's a bit more bare bones at this stage. But I did manage to get some profiling done, and it turned out that about half the time was spent running in the random number generator. Rust tries to be safe, so the normal random number generator is cryptographically safe. So it is a really good random number generator. For these creatures to decide whether they want to eat or sleep or turn left, it didn't have to be safe from a cryptography perspective. So I went for a very simple XOR shift random number generator, and that gave a lot of the speed up. that may have, had I done this in hindsight, might have speeded up the closure version a little bit too. I don't know, I never profiled this. I will be honest about that. I don't have scientific data. This, again, probably would be another talk, but I do want to leave you with at least a view that I wasn't the only one to see this. There's Brian Cantrell, the author of dtrace. I don't know whether you know it. It's a tracing tool for understanding Linux and other Unix-based operating systems. And he had written an analysis tool. And he was in a similar state than I. He wanted to learn Rust, and he took what he knew and implemented it. And that's what his experience was also. Again, a very experienced C programmer. So a little bit like myself. I was like, yeah, as long as the compiler doesn't spit out these page-long errors and my unit tests are passing, it's probably going to be all right. And he was in a similar situation. He knew the problem domain, he had the code, and he was just basically translating into Rust. And that's what he left with. Interestingly is the findings also from that blog article. So this is a 229 megabyte file, about 4 million state transitions in there. The first implementation he had was purely in JavaScript. And I can't resist making that joke again. Whenever somebody says Node.js is blazingly fast, they've probably never seen anything but Node.js. And that is also what Brian, of course, knew. So what he did is that was unacceptable to him. 83 seconds was just like, that can't be right. So what he did is he rewrote the core processing loop in that Node.js in C, and the most of the JavaScript code was just calling the core C function. That gave him this result. So 99% of the runtime here is now in C. The Node, the JavaScript part is just the wrapper around it. And remember, now what he said was, he just tried to get the Rust version working somehow without the optimizations or anything else. And that's what ended up being the case. He spent much more time than I, apparently, looking into what the compiler does. Interestingly, I didn't mention this, Rust also uses the LLVM, the low-level virtual machine that is also C and Swift. So it has the same backend, and yet oftentimes it actually comes out faster than C code even. And he had some theories around why or how the CPU was used, how certain parts of the CPU were utilized to actually get a better execution profile than even more or less native C code. And that is all I had for you, but I do have time, I think, for some questions. Thank you.